Hi all, this is my video number 12. Right, so I'll talk on the concept of supremum and infimum. Yeah. Supremum and infimum. So what is supremum and what is infimum? So let's me begin with this. Let's say we have a sequence, a convergence sequence. Let's say we have this increase and bounded, and let's say we have another one decrease and bounded. Let's say I have this. Yeah, just to begin with. Okay, now if you look at this sequence here, is increase and bounded. We can see that none of the element of those sequence will exceed some numbers. Let's say this number m. Yeah, will not exceed that number. So the same thing with the decreasing sequence and boundedness. You can see that this sequence will not goes beyond than that, let's say, small number m, or even you can put the negative part, even you can. Yeah. So now from here comes the terms that what we call as a upper bound and lower bound. Okay. Even in this case, we also have lower bound here. All right. The sequence will not goes beyond than that point, as well as this part here. So this part we say, in this case we say m is upper bound. All right, and in this case we say m, small m, as a lower bound. So that's the concept of upper bound and lower bound. So in formal writing, let me write those things. All right. If we consider a set of real number, right? So let x is a set of real number. Set of real numbers. You know what real numbers is? Set of real numbers. On the x axis, you may consider any, but just take one part of it. Maybe here, just that. So either open or closed set is still okay. Okay, this is just one of the example. Now we say a number m. This is a. This is a number m, capital M, is upper bound of a. Okay, if x, any number x within that set is less than m. So in this case we say m is upper bound, yeah, for all x in a. I'll give you an example in a minute. And then if we have, okay, now look at those upper bound. Okay, if we can find some alpha prime, m prime, for example, very small, let's say m prime here, where the distance between that and that, let's say, some small number epsilon, okay, some small number epsilon, such that we say m is least upper bound. We call m is least upper bound, least upper bound, if for any small number epsilon, then m prime, which is m minus epsilon, is not an upper bound. It's not an upper bound. An upper bound. Okay, so let me describe this part here. So we have a, let's say, those sequence. I just try to magnify those part. So we just take those. So let's say our m here. Just consider our upper bound where our sequence is somewhere like that. Okay, if we have m prime somewhere here, where m prime is, we deduct from m as much as epsilon. As much as epsilon. So what happened is that with that deduction epsilon, there is term in that sequence lies between m prime and m. So which means m prime is not the upper bound, but yet still not surpass or not exceed the value of m. So in this case, m is least upper bound. Hope you can understand those things, because okay. Now let me try to make it as simple as possible. There are many upper bound for this sequence. Many upper bound. You can consider here, let's say m1. This is also upper bound because this sequence will not exceed this. But definitely, if you compare m1 and m, of course m1 is much bigger than m. But m is still upper bound. Yes, m1 is upper bound, but m is also upper bound. So m, we call it as a least upper bound. As long as there is no element of that sequence exceed, even a single element exceed the value of m. So we call that least upper bound. So that's why we have this m minus epsilon there. So the similar things. So this least upper bound, we call it as a supremum of A. Supremum of A. So let me call this M, and we denote that supremum as A as a supremum A. In your note, they use M prime, whereas M prime in my case, I put m minus epsilon. So m prime is not the upper bound anymore. So now the upper bound in this case is m. Okay. Now similarly, we can describe the same thing for the lower bound and the greatest lower bound. So for the lower bound, we say m, small m, is the lower bound of a set A if we have m not greater than x for all x in A. And if m minus epsilon is not the lower bound, then we say M is the infimum of A, or the greatest lower bound. We got the greatest lower bound, greatest lower bound of A. Okay, greatest lower bound of A, and we call this as infimum. So we write M is infimum of A. Again, you not use M prime, because consider M prime is smaller than M and is still a lower bound. In my case here, we have deduct M with M minus epsilon with a small number, then M minus epsilon is not lower bound, so we consider M as a greatest lower bound. So I denote that M as a infimum of A. Alright, so there is some what they call as a completeness axiom, completeness axiom, which is say that if A has an upper bound, then A has a least upper bound, supremum. Right? Completeness axiom. Completeness axiom, which is if A set has an upper bound, then A has supremum. Then A has a supremum. So we denote that as a supremum as A. So denote as supremum of A. And number 2, if A has a lower bound, then A has an infimum. We denote this as a infimum of A, inf A. Okay, hope you can understand this concept. First, the concept of upper bound and lower bound. You know that bound of a sequence. We say a sequence is bounded. You understand what we mean by sequence is bounded. Then we come up with notation of or term of upper bound and lower bound. Now, with those upper bound and lower bound, we have least upper bound, we have greatest upper bound. So differentiate those things. Least upper bound and greatest lower bound. So now let's see a few examples to describe those supremum and infimum. Okay, look at this example. First, we consider a set A with interval close interval 0 and 1. Interval 0 and 1. So if you look at this interval 0 and 1, which is include 0 and 1, alright, so in this case, the maximum element in that set is 1, and the minimum or the smallest the smallest element of the set is 0. Alright, so in this case, we say the supremum of A supremum of A is 1. And infimum of A is 0. If we just consider upper bound, if we just consider upper bound, well, 1.1 is upper bound of A, 1.1, because it's outside D, and none of the element of A will exceed 1.1. That's also upper bound, but we are looking for the least upper bound. So 1 is the least upper bound. Okay? Now let's consider the second example. If we consider set A is 0 and 1, half open set. So in this case, the supremum of A is still 1. Supremum of A is still 1. What about the infimum of A? It's 0, right? Even though 0 is not in the set, not the element of set A, but you can choose any small number that close enough to 0. So 0 is the infimum of A. Alright. Of course, there are many examples. If you want, I give you one more. So if you have say A, this set here, 1 over 2, 1 over 3, and so on, 1 over n, and so on. Okay, so obvious from here, the upper bound is 1. The lower bound, so look at this, is getting smaller and smaller. The denominator is getting bigger and bigger, and therefore the terms become smaller and smaller and smaller. But since n is always positive, no matter how big you choose n, alright, none of those terms will go beyond than 0, or lower than 0, or smaller than 0. So in this case, we say supremum of A is 1, and infimum of A is 0. Okay? Now, if you look at all these example, now let me consider one more example. We consider the open set. Let's say 0, 1. Open set. In this case, supremum of A is 1, then infimum of A is 0. Now compare this, especially when 1 and 4. Look at 1 and 4. Look at example 1 and 4. Okay, if you look at the example 1 here, you can see that the supremum as well as infimum of A both contain in the set itself A. Look at this supremum A, 1 is in the set, and infimum of A, which is 0, is also in member of that set. Whereas if you look at this example number 4 here, supremum of A, which is 1, is not in the set because this is open set, so 1 is not in the A. 1 is not in the A because this is open set. And as well as infimum of A, which is 0, 0 is not in the A, so which means the supremum of A, infimum of A lies outside the set A, as compared to the first example there where supremum of A and infimum of A lies inside the set of A. In other words, what we can say, the supremum of A and infimum of A not necessarily contained in the set A itself. Yeah. So let me write that as a note. Okay. not the supremum. Let's say supremum, just make it in general, any set, supremum of A and infimum of A are not necessarily not necessarily contained in A. Not necessarily in that set. So now it is important, let me stress again, the supremum and infimum. Okay, as I mentioned earlier, that we begin with the concept of boundedness of the sequence. Boundedness of the sequence. Then we introduce with the upper bound and lower bound. You know what we mean by upper bound and lower bound, where none of the element of the sequence or set or sequence exceed bigger than the upper bound or smaller than lower bound, none. And then we come up with the concept of least upper bound, where you have a very small number that none of the element of the set exceed that number m that we choose. So everything still contained under those upper bound. So we call that as a least upper bound or supremum. So similarly, we can define for the infimum. Okay, so that's the concept of upper bound and lower bound, least upper bound and greatest lower bound. Now let me go to the limit of superior and limit of the inferior. How can we find this limit? Okay, so limit superior and limit inferior. Okay, what is this and how can you find this thing? Okay, now let us suppose that UN is a bounded sequence. Is a bounded sequence. Okay. Now we define. Just follow this. We define Mn as a supremum. So you know what supremum now. Supremum of, we have UN plus 1, UN plus 2, and so on. And this can be written as supremum of UK k greater than some number n. This is same meaning. And we define small m n as an infimum of UN plus 1, and so on. We denote this as a infimum of UK for k greater than equal to n. So remember that we have a sequence UN which is bounded, and we define the supremum and infimum of those sequence, then if we develop from here, you can find M1 which begin from U1, U2 and so on. You can find M2 which begin U2 and so on, and also M345 as well as small m1, m2 and so on. And from there we can construct the sequence of those supremum, sequence of the supremum, which is M, is, since U itself is bounded, sequence itself is bounded, then the sequence of the supremum of those sequence is also bounded, is bounded, and decreasing, increasing, because in this case M is this, the lowest or least upper bound, so this is bounded and decreasing, all right, and sequence of small m, right, the infimum, is also bounded and increasing. Then if the limit of those sequence of supremum, sequence of infimum exists, then we call it as a limit superior, limit superior of that sequence. Okay, so if the limit of Mn that exists, which means limit exists, which means if we take a limit of those Mn, n goes to infinity, give you some numbers. Let's say, I don't know, let's say just put the M. So which means the limit exists. So we call it as a, as a limit superior of the sequence. Limit superior of the sequence Un, because we obtained it from the sequence Un, and we denote this limit superior, we denote as lim supremum U of k. Of course we take a limit k goes to infinity, alright. So this is just the same as limit for k goes to infinity, n goes to infinity. We have supremum of uk for k greater than n. Alright, which is also, if you look at this, seems supremum of uk is we define as mn. So lim sub, which means this is lim or limit of mn. N goes to infinity. So we develop this definition or terminology from boundedness, upper bound, least upper bound, which is supremum. Now we come up with the limit of the supremum, or we call it as a lim sub. Limit of the, we call it as a limit superior, which is lim sub. We can do the same for the limit of the infimum. Yeah, we can do the same for the limit of infimum. So let's do that one. We'll give an example later on. I hope I have explained clear enough to you to understand those concepts. Then we strengthen your understanding with the example a little bit later. All right. So now look at the another definition of what is the lim infimum. We have defined lim sub. Okay. For lim infim, so if the limit, let's say the limit of this sequence exists, what does it mean? It's the limit of the infimum of the sequence. Yeah, mn is the infimum of the sequence. We have defined that at the beginning. Here we have mn is the infimum of un. Okay, what is infimum? You know, infimum is the greatest lower bound. So if the limit exists, means that if you take a limit of mn, n goes to infinity, we can find some value here, small m, say. Okay, so if those limit, we call that as a we call that limit. We call that limit as limit inferior. Yeah, limit inferior. Inferior. Okay? Limit inferior, which is limit of the infimum of the sequence, and we denote that as a limit of infimum of uk for k goes to infinity, and this is just the same as limit n goes to infinity infimum of uk for k greater than n, and we denote this as a, also can be denoted as a limit of n goes to infinity mn. You know that mn is the infimum of the uk. All right. Yeah, I hope that not too heavy for you. This is still a simple basic concept for you to understand. Right, now let's see a couple of examples. Yeah, let's see a couple of examples. The important part that you need to remember is this definition here. This is quite important because we need to find what is m1, m2, m3 in order to find the sequence of mn. Yeah, in order to find the sequence of mn. Now, look at the example. We want to determine the lim sub and lim inf for the sequence. Yeah, determine the lim sub and lim inf for the sequence un, where un will be given in a minute. Okay, so now having understand all those concept of lim sub and lim inf, so normally when we put lim sub like this in many book, all right, they don't put the n goes to infinity or k goes to infinity, n goes to infinity here. It's understood that those n must go to infinity. Okay, so now consider our un. Just first example, consider our un as a 1 over n. So which means our sequence un is sequence of 1 over n, Yeah. At the beginning we note this n equal to 1 to infinity, but now we understood that when we say it is a sequence, then n must be from 1 to infinity, cannot stop anywhere in the middle. Okay, so we have this. If we list down this, we have 1, 1 over 2, 1 over 3, 1 over 4, and so on. 1 over n, and so on. Okay, now remember that in order to find lim inf, first we need to find supremum itself of un, and then we define the supremum as a mn. Now let's do that. Okay, now we suppose that, or we define or suppose that mn is a supremum of un plus 1, un plus 2, and so on. And do the same because we want to find lim infimum as well. So and we also define small m n as a infimum of un plus 1, un plus 2, and so on. Okay, now using those two definitions, what we have, you can write down m1 from those. This is supremum of. Now, what is u1? So when you see u1 in this case, this is your u1, this is your u2, and so on. So your u1 is 1, u2 is half, next 1/3, next 1/4, and so on. Alright? So you can see from here the supremum of that element, 1/2, and so on, is 1. It cannot go beyond than or greater than 1. Alright? Now, we're looking for m2. M2 supremum of, okay, so it begin with m2, now u2. u2 is half. So it begin to with half, 1/3, 1/4, and so on. And in this case, supremum of those, look at the biggest number there is half. So this is half. Alright? So by doing this, you can proceed that. You can find m3 is 1/3, n4 is 1/4, and so on. And later on you got m, and this is 1 over n. So now your sequence of mn, so therefore our sequence of mn, sequence of the supremum is 1 over n. Now, therefore, if you want to find the limit of supremum, of un, this is nothing more than limit of mn itself, because mn is the supremum of un. You just substitute this, you got this. And we know that mn is 1 over n, so we have this limit 1 over n. Of course, n goes to infinity, so that gives you 0. So we find the lim sub of the un is 1. Is 0. So you can see from this example, this particular example, that the supremum we take the upper bound. The supremum we take the upper bound, but when we take the limit, it goes to the the smallest, yeah, because of the nature of the sequence itself. Now, having done that, you can also find the lim for the sequence. Now, we come to the definition again for the infimum. Okay, that definition we have mn is equal to infimum of un plus 1, and so on and so forth. So let us try to find each of those elements of mn. So by definition of, we define those things, mn, so you can find m1. m1 is actually infimum of u1, which is 1, u2, which is half, u3, u4, and so on. 1 over n, and so on. So in this case, the infimum is the lower bound, the greatest lower bound. So if you look at this, and when you increase n, when you increase n, it will come close to 0, but not actually 0. So you can say the greatest lower bound is 0. Alright? And you can find m2 by doing the same. m2 is infimum of, we have half, 1/3, and so on. You also got 0 here. And then later on, up to n term, you also got 0. So therefore, if we take limit infimum of un, this is equal to limit of mn. This is just limit 0. This is 0. Okay, so we have found the lim sub and lim in for the sequence. So you can try other example. So let me give you one more example. There are a few more examples in the note, so I think you can read by yourself those examples. So just let me give you one more example. Let's say try to find the repeating one. Just a minute. Oh, this one negative positive. Okay, I consider this example. Okay, let's say we have our un is given as -1 to the n over sub n. So our sequence un, if you list down this, so what we have, this is sequence of those. This is when n equal to 1, you got -1, you got positive 1 over sub 2, you got negative 1 over sub 3, 1 over sub 4, 1 over negative 1 over sub 5, and so on. Remember that we want to find lim sub and lim infimum. Again, we begin with we define mn as a supremum of un plus 1, and so on. And we also define small mn as a infimum of un plus 1, and so on. Okay, so having done definition, we define mn and mn, m capital Mn, small mn. Then from there we can find what is m1, m2, m3, and 4. So therefore for m1 is supremum of our u1, because we are looking for m1. So u1 is -1 and follows those things. So -1, 1 over sub 2, we have -1 over sub 3, and so on. Alright? And it is obvious from here that the supremum or the least upper bound is the biggest one, is that one. which is 1 over SUT2. Alright. Now if you find M2 is a supremum of, it begins with the second element, which is 1 over SUT2. So we have 1 over SUT2, 1 over negative 1 over SUT3, 1 over SUT4, and so on. So this is, you got, the biggest is 1 over SUT2. Now by doing this consecutively, you can find what is M3. You got M3 is 1 over SUT4. You got M3, M4 is 1 over SUT4, and so on. Alright, M5 is 1 over SUT6. M6 is 1 over SUT6, and so on. So from here, look carefully. If you rearrange this to give you the sequence of Mn, so what you got is 1 over SUT2, next is 1 over SUT2, next is 1 over SUT4, 1 over SUT4, 1 over SUT6, 1 over SUT6, and so on. Yeah, I think we have, or I have explained, or I have give you many examples on how to find the general terms when given the list of elements of the sequence. So in this case here, what we do is look at where the item or the element start to change. So here, first and second element doesn't change, but third element change. So we comes from 1 to 3. So look at that. Next, you go to 5. Next, you go to 7. What is it? So you have 2n plus 2n plus 1. Whereas the other one, you have this 2 to 4. Alright? 4 to 6. And next, 8, next n. So increase 2 by 2 by 2. Okay? So from there, you can have a general terms of Mn. You can have a general terms of Mn. So we have M, for this is the first term, and then third. How to get that? 1, 3, 5. You got 2 n minus 1. Okay? When n equal to 1, you got 1. When n equal to 2, you got 3, and so on and so forth. So this give you what? That, which is 1 over n, 1 over 2n, 1 over SUT2n. And you can have M 2n. This is also 1 over SUT2n. So this we take from the even terms. So therefore, the limit of un, lim sub of un, this is equal to limit of mn, this is equal to limit of 1 over SUT2n, which is 0. Alright, so hope you can understand those things. Now, that's for the lim sub. For the lim inf, for the same example, alright, we define mn, small n, as infimum of un plus 1, and so on. With this, you can find what is m1. Alright, your m1 you got minus 1. M2, I think if you cannot see this, please arrange that value. Arrange that. So M2 is negative 1 over SUT3. M3 is negative 1 over SUT3. Yeah, M4 is negative 1 over SUT5. M5 negative 1 over cert 5, and so on. Thus, from there you can find the general solution or general terms, which is m 2n. This is negative 1 over cert 2n plus 1. Arrange those m1, m2, m3, m4, m5. Arrange that so that you can see the general terms. If you just look at like that, maybe it's not that clear enough especially for you who just start to learn. Yeah, for beginners it might not easy to see, but when you arrange that, then you can see it. Then next is you have 2n plus 1. This is negative 1 over 2n plus 1 cert. Yeah, for all n. Therefore, you can find the limit infimum of un. This is limit of mn. This is just limit of negative those things. So negative 1 over 2n plus 1, that gives you 0. So we have now the lim supremum is 0, and as well as lim infimum also 0. There is one more example in the on your notes. I think you can learn by yourself based on what I have explained here. If you say you have any problem, you can just message me anytime, no problem. I will try to respond to you. All right. So again, let me stress what the important thing that we have learned today is that on the terminology of limit of supremum, or we call limit of the superior, and limit of the inferior. It's begin with again I repeat this thing, begin with the concept of boundedness of the sequence. Then we reduce the scope to the upper bound and lower bound, and then we go to the least upper bound and greater lower bound. That comes the terminology of supremum and infimum. Now, having obtained the supremum and supremum of the sequence, construct the sequence of supremum and sequence of supremum. From there, we can find the limit of the superior, or we call it as lim sub, and limit of inferior, we call it as a lim inf of the sequence, of the given sequence. So with that, I stop here for this video. Thank you. Bye-bye.